So thank you very much, Sibghat Ullah Sahab, for joining this session on AI applications. How do you say about this, please?
Yeah, so there are numerous applications for the AI, but the one that, at least the one where I have spent a lot of time, focus a lot on the industrial optimization. So think about Industry 4.0, that's fourth industrial revolution. Typical applications in this field are, for example, automobile manufacturing, steel production, building construction. Yeah, those are some of the very common applications for AI. And the core of the AI here is obviously search and optimization. So coming up with the best possible solution from a given array of solutions in a in really the most possible efficient manner. So yeah, basically in this talk, I'm going to describe one of the very interesting issues that we face when we are doing this optimization, when we are applying AI for industrial applications, like the one that I have described before. And one of the most common issues here is dealing with the uncertainty and the noise within the optimization setup. So that's essentially the core. Yeah, that's essentially the core of what we're going to talk today. Um, yeah, about myself, just a brief introduction. My name is Sibghat Ullah. I have a PhD in computer science, and I have spent some time understanding these robust optimization models, and yeah, also working with some of their applications, especially in automobile manufacturing. So I'm currently also a Renewcast co-founder, which is Renewcast is an energy startup. It's a renewable energy startup, and the focus of this startup is basically to provide the forecasting services to the independent power producer throughout Europe. So yeah, so that's a little bit about myself. Let's go here and let's see what we will have. I will first describe the aim of robustness. So I will first describe why do we even need this robustness, meaning dealing with these uncertainties, these noise. Why is it even important? I will then give a brief overview of how it works, basic sketch, but that's the basic sketch. There's an algorithmic family, if you would. Then basically from there on, you can always tune it up a little bit. I will then describe how do you actually achieve this robustness in practice. What are some of the most common formulations for this? And the most important question here, which is the crux of the talk, is basically how do you in practice pick up the right strategy to deal with the noise and the uncertainty within the optimization scenarios. And that's basically is to say how do we pick the right strategy for robust optimization. So some key questions related to that. I will describe some of the test or empirical studies that we did ourselves, some results, conclusion, major takeaways, so on. So without further ado, let's go to this figure. So this figure one, it's really interesting. It basically encapsulates the core of what the optimization in practice is. You start with this. You start with these design parameters, input parameters, search space X. You can refer. You can denote it any way you want. But the point is that this describes what are the input parameters that you will change so that the system is optimized. And then there is this alpha, which is usually ignored in the system. I included it, but you can also ignore this. This is just to say that every time we come up with the optimization scenario of a system, anytime we come with the optimization scenario, the point here is that there are external conditions, environmental parameters that are always there. And those external conditions, those environmental parameters can also affect the way the model or the system behaves. So for example, we all know, for example, not every car is built for each kind of scenario. Like certain European cars, for example, you won't see a lot on Pakistani roads. That's because they are not built for Pakistani roads. That's because there is an external factor, the conditions that essentially dictates um, the these parameters, these external conditions can have a lot of impact. Basically, together, both of them, they produce some output, which is called y, and this output then describes two things. Objective functions, which are described, for example, a list of objective functions 1 to k. You can have one, you can have two, sometimes you can have multiple. For example, in the car optimization scenario, on one side you want to minimize the fuel consumption, and on the other side you want to optimize the handling, for example, or the comfort. So you have multiple objectives. These G1s, these are basically constraints. You can also ignore it for the sake of simplicity, that we will not have any constraints. Of course, in practice, there are always many constraints. So for example, you will have a constraint. For example, the car has to go, for example, the car cannot go above, 200 kilometers. Or for example, the car has to have a minimum mileage consumption, for example, 4 liter, 5 liters for each 100 kilometer. So an average like that. So this is typically the optimization scenario. The point here is that you have some inputs, some design parameters. You put them into the system. You have a value, and basically based on that, you go into the loop again to your optimizer. This optimizer is basically an algorithm. It's for the sake of abstraction, I'm just calling it optimizer, but this is any standard optimization algorithm that will basically tell you, what's the next iteration. So then you will have new settings for these X or these. So the point here is this: in typical optimization scenarios, this X that you see, these input parameters, these search space, these design parameters, whatever you call them, they are assumed to be the fact that whatever you will have in theory, you will also have in practice. But that is not always true. For example, if you have certain parts of a car, in theory, they would always say, for example, the rim of the car is, for example, 16 inches in diameter. But in practice, it's not always 16. It's 15.999 something or 16.111 something. It's never always 16. And we know this because we have studied this a lot. This is never, whenever you have something that is produced on an industrial scale, mass production, there is always an economic sense to it, economies of scale. So you cannot always have exactly, what you can describe in mathematics, in theory, you won't always have that. So what does this tell us then? Well, it tells us that whatever we are describing, this X, in reality, in practice, it won't always be an X. There will always be some uncertainty. There will always be a delta X here. And that's essentially the way we say that. That's uncertainty, that's noise. Different parts of the system that come together are not always what is described in the manual. There will always be subtle changes in that, and you want to account for that. Why do you account for that? Because there are some applications where you cannot, where you cannot accept failures or tolerate failures. I'll give you an example. For if you're designing a nuclear reactor, you cannot leave anything to chance, right? And similar, for example, when you are designing a car that you want to be extremely safe, there are multiple car brands, right? For example, Volvo is essentially their core business is around safety. That's all there is. They say we are better than anyone else when it comes to safety. We are the safest car ever. So for those kind of applications, for those business requirements, this X has to be, you have to account for the uncertainty, you have to account for the noise. In some applications, if you're, for example, producing a table lamp, you don't need to care about that. But some applications, in defense applications, when you're designing fighter jets, when you're designing aeroplanes, when you're designing cars for safety, you have to account for these things. That's why that's the business need, right? So that's why we're discussing it. Otherwise, for normal applications, it's fine to even ignore them. All right. So the way that the algorithm or the workflow here is, we basically, the first job for us here, if I go back to this slide 3, is to model this uncertainty and noise, this delta X. How do you mathematically represent that? So you can represent that here, for example, in step 2, either in the form of a probability distribution. For example, you can say, I have sufficient evidence to believe that there will be some noise, but I know what will this noise be like. So maybe it's coming from a normal distribution, maybe it's coming from a uniform distribution, maybe from another probability distribution. And how would you know this? Well, you always have domain experts to help you. When you are designing some things of that scale where you cannot accept failures, then you always have domain experts. So in the case of this, for example, you have many mechanical engineers, a team of mechanical engineers that will tell you we cannot accept failures, but we will tell you how much we can change in practice. So you will have some help there. The third step here would be, okay, you have an uncertainty, you have a noise, you have modeled it probabilistically or deterministically in the form of a set or something. But what do you do now? And that's the point here, is that you choose what do you want to do, what is your objective now. Sometimes your aim under the uncertainty and noise is to optimize the worst case scenario. And sometimes you want to optimize the average behavior. All of these things, this is what you design in step 3. This is also a little bit related to business. So your business sometimes dictates which one of these would you choose. The fourth step here is, okay, you already have modeled uncertainty, you have already modeled noise, you already know what are you going to do, and you basically now come up with a new objective function as opposed to what you defined before. And then basically in the fifth step, you can solve this robust counterpart of the original problem. You can solve it with any optimization, standard optimization algorithms, usually with direct search algorithms like surrogate modeling, evolutionary computation, genetic algorithms. They're really good, especially in practice. And basically, the process comes to it. That's how in practice you have if you have uncertainty and noise in a problem, this is how you handle it. This is a basic template. Then let me go to let me describe here this step 3 here, this robustness formulations. The point in step 3 here is to say you can already describe the uncertainty and noise in the form of mathematically represented. What do you do now? That's step 3. So what you can do now is basically you can have, for example, some of these scenarios that you can adopt. One would be preparing for the worst case scenario. And as I said, defense applications, designing a fighter jet, designing a missile, designing a submarine, designing a nuclear reactor. These are just some examples, but you can think that there are some applications in industry where you want to optimize the worst case scenario. So if there is a noise, what is the worst possible thing that you can do? And then try to optimize that. That's the point. Then there is the minimax regret. This is not very common, but I picked this up because this is a historical baggage. It has been used historically. This is to say basically, I want to minimize the maximum regret, and mathematically regret is the difference between the most optimal solution that you could have under the uncertainty versus what you have now in reality. So that's the regret, and you want to minimize that. In other words, you want to be as close as possible to the original problem. And then there's expectation-based or dispersion-based or composite. Expectation-based means you just want to optimize the average behavior. Right? You have uncertainty, and noise. You don't want to optimize the worst case scenario. You just want to optimize the average behavior. And then you have dispersion-based. This is to say that you want to minimize the unpredictability or the variance. Like if there is an application where you are saying, okay, there's an uncertainty, there's noise, I know that. But in practice, my customers they want a really solid, reliable solution. So I don't want a lot of changes. If it doesn't work for whatever reason, I don't want to end up where my clients face really bad repercussions. So you want to be basically you want to fix it. You want to be static. You want to minimize the variance, the unpredictability of it in the outcome, that is. And then it's also composite. You can also combine any one of these together in any way you want, and that's composite. That's in general, this is basically between expectation and dispersion. So that's a balance between both of them. So these are some of the common scenarios what you can do once you know how to describe the uncertainty and noise in a mathematical manner. These are some mathematical representation of what I described here. I would avoid this for the sake of argument, because this is just bombarding with a lot of technical information that's not useful. Because in this talk, what I want to do here is I just want to give a flavor of what it's like. I just want to give the essence of the principle rather than these mathematical details, because you can always find it online anyway. So there's just no point uh, explaining all of this mathematically. They're quite straightforward. In essence, you want to remember this. This is more important than coming up with the mathematical description. So for now, I will just avoid this unless someone is really interested and wants me to explain this. Then I can come back. Okay. So then, okay, we have some of these common scenarios that we can adopt, but which one do we pick actually in practice? That's a question, right? Um, and So basically, this is saying, how do we pick the right strategy in practice? Which one of that makes more sense in practice? So what you want to look then in that case here is you want to look at the computational budget you have. You might not have a lot of computational budget. Sometimes you have more, sometimes you have less, but it's an important thing. Then the other thing that you want to look here is that the compromise on optimality. And what I mean by this is your original problem was something else. There was a different problem landscape. You have now changed it, right? And you will now end up with something else. And that something else may have a higher optimal point, and you want to minimize that. So you are compromising on optimality, because new landscape could be, and it often is, a little bit higher, because the uncertainty, this delta x that we saw in the past, is additive in nature. So that means that there's always more. And also, of course, the characteristics of the new problem landscape. If you have a lot of domain help experts, then they can always tell you which one of these you can pick in practice. But most of the time, you won't have this information. So this is all of these three main reasons or factors for choosing this right strategy. Assume that you don't have a hard constraint on the choice of robustness formulation. In other words, nobody is forcing you, or because of your problem, you are not forced to choose one of them. You have an option. And if you have an option, then you can come up with looking at these factors, and then you can come up with some of these. What we want to look now, however, is most important. So it's to say, if I only look at computational budget and nothing else, which one of that makes more sense? I don't care about, for example, for the sake of argument, I don't care about optimality, problem landscape, none of that. I only care about computational budget. In other words, I want to pick up a solution that will give me, I want to pick up a strategy that will give me an answer in the most efficient manner very quickly. And so computational budget is the main problem that you have. If that's the case, then there has to be this is the problem. This is we try to find the solution for this problem exactly. So what you see here are quite standard functions, and these are test problems from BBOBs. This is a test suite for optimization. BBOB is very standard, very benchmark, at least in academic circles. And yes, from there we picked some of these functions. Again, describing these functions is very relevant. You can just Google BBOB and you will already know what these functions are, what is their problem landscape. But in any way, these are quite challenging, objective functions, quite challenging landscape to optimize for. What we also try to do here are different settings for noise level. So 5%, 10%, meaning, for the sake of argument, if your original design parameter was supposed to have a value of 100, then 10% deviation means it will now have a range between 90 and 110. So now instead of having 100, you are between 90 and 110. And now you have to come up with the optimal solution between that. So dimension is basically the dimensions of the test problems. Each one of these problems that you see here, F2, F3, F7, whatever, each one of them is generic enough so it can be described for multiple parameters. We choose for each one of them 3 settings, 2, 5, and 10. That's small to medium. That's not high dimensional problem. But then again, we're not focusing here on high dimensions because that has separate field of its own. So, and we basically did 15 runs just to come up with an average answer, if you would. All right. So these are some of the most interesting results that we find. Let's go to figure 3 first and foremost. Um, sorry. So in this figure 3, we have the red one, the red curve, the MMR is basically minimax robustness. This is the worst case scenario. You know, we already described what are um, some of the most interesting robustness formulation. This was the first one, preparing for the worst case scenario. Then we had minimax regret robustness, described here as blue. Yeah, this is described here as blue. Then expectation-based robustness is green one. This is just the average outcome. Then there's dispersion-based robustness, which is black. It's basically the variance that we saw before. And composite robustness is just a green and the black one are combined, and then we have a pink one, orchid one, called composite robustness. So that's just what each curve is representing. Then we have here 4 plots. Let's look at the leftmost one on the first row. Here we have fixed CPU time analysis. In other words, what we are saying here is we're describing how many number of seconds you have. For example, we fix it to 10 seconds. Let's say, for the sake of argument, 10 seconds. Then which one of that then come up with the best possible solution? This NMAI is basically normalized mean absolute error, and you want and basically what you want each one of these curves. These are empirical distribution function, empirical cumulative distribution function. In other words, what you want these curves to be to converge to one as quickly as possible, meaning as much possible as to the left. If something is if a curve is going to the right, it's not good because it's taking a lot of time, right? Or in the case of normalized mean absolute error, it has a higher error. So when you look at the first column, first row, fixed CPU time analysis, you see that the dispersion based or the variance space has a higher error, meaning this is not a suitable one in this sense. The other ones are mostly similar. Then you have a fixed iteration analysis. Here you are saying I don't hardcode the number of fixed CPU time that anyone can have, not the maximum CPU time, but I will tell you how many maximum iterations each one of these curves, each one of these algorithms can. So for example, 50 iteration, say for the sake of argument. Then after 50 iterations, I will look at the error for each one of them, and the one that is that has the lowest error is good. So this is again empirical cumulative distribution function across all 15 runs. And here you see the blue one, the minimax robustness, minimax regret robustness, the blue one, it converges faster than the others. Dispersion-based robustness or variance-based is also bad here. And then if we look at the second row, fixed target analysis, then here we say, I don't fix the CPU time. I don't tell you how much time you should take. You can take whatever maximum time you can take, and you can take as many iterations as you want. But I fix the error, and I want this error to, because you want to minimize the error. So you for example, we have said that this is a fixed error, reach this error, and whatever reaches it quickly in CPU time is, gets a candy, wins. So that's the red one. Then we see that if we fixed the target, if we say this is my target to the actual real optimal solution, the difference between that's the error. So you and I can accept a certain error, but reach that error, and you can take as much CPU time as you want. And here you see the red one converges faster. In other words, it takes less number of CPU time to reach that target. Whereas if you look at the same curve, the blue one takes way more time, way more number of seconds to reach the same target, right? That's the point. And this is the fourth one, basically second row. and the second column is the running CPU time per iteration. This is to say, okay, each one of these algorithms, each one of these robustness formulations, once I put in and run the algorithm, I already described the algorithm here, just for the sake of argument. This is not really algorithm, but this is essentially the crux of the algorithm. So you can treat it as algorithm for the sake of argument. Then if I put these in the second step, if I put these uncertainty that we were seeing in that graph, then we run this and basically we come up with the answer that we were showing. So here you are saying if I put these each one of these robustness formulations, average time per iteration of the algorithm, how much time that is. And as you see here, the minimax regret robustness is quite high compared to the other ones. So what we see from here, at least it seems to me that the red one is mostly good in most of the scenarios, whereas the black one and the blue one are definitely not good, because in the first row they lead to higher error, and the second row the blue one leads to a lot of time. So that's not desirable. The red one is mostly good enough. If we look at the figure 4 here, this is just to say what is the maximum CPU time for each one of these runs. We had 15 runs, so this is an average of 15 if you would. But here you are saying what is the maximum of this CPU time for each one of these runs. And here you see you have 3 graphs here, D2, D5, and D10. Each one of them basically describes the dimensionality. Dimensionality can have a lot of impact when comparing these kind of, within this kind of empirical studies, because, so you want to test it for multiple dimensionality settings. And here, for example, you see again that the red one is quite low compared to the other ones. Even for 2-dimensional problems, the maximum CPU time for each one of these runs is quite small compared to the other ones. Whereas look at the blue one. The blue one takes a lot of CPU time, even for a 2-dimensional problem. For example, it takes 2 raised to power 11 seconds on average, and the maximum CPU time, even for a 2-dimensional problem. That's not good enough. Then we look at 5-dimensional problem, and we see similar settings: expectation-based robustness, which is green one, and the red one, minimax robust. That's worst case scenario. That's still good enough. And also, if we look at the 10-dimensional, we still see that the red one is still quite competitive. Although there is someone which is when you increase the dimensionality expectation-based, look at this expectation-based. This is a little bit lower compared to even the red one. However, it does prove that the expectation that this red one is still good enough in most of the scenarios. So that's basically the crux of the results. Without going into too much details, the point here is that this red one is mostly good enough in both of these figures, honestly speaking. So one of the conclusions that we can draw here is that these are all good robustness formulations, but it depends what is the designer, what is the engineer want to get. So, for example, the minimax robustness is suitable if the designer cannot afford the quality of the solution, but he can afford the number of CPU times. So, for example, if the designer tells, I cannot afford on the quality has to be good enough, but I can compromise on the computational budget, I can give you more time. If that's the case, minimax robustness is the best one. And it's also usually minimax and expectation-based, average-based robustness also perform excellent in terms of average CPU time and maximum CPU time. Minimax regret robustness, this blue one, is usually bad. It's usually not good enough. And that's actually the reason why it's no longer used in common optimization or such scenarios, because it's basically there is a triple nested loop for the optimization here. It usually takes a lot of time. And usually the lower variance in the CPU time to run the algorithm for expectation-based, dispersion-based, and composite robustness. One interesting thing that you will see here is the maximum CPU time for each one of these runs increases rapidly when you increase the dimensionality. Like, for example, even each one of them, if you look at comparable, for example, look at this figure 4 and look at this red one. For two-dimensional problem, it takes 2 raised to power 8 seconds. And for five-dimensional problem, it takes between 2 raised to power 11 and 12. And for 10-dimensional problem, still 15. But you're seeing that the dimensionality is playing a role here. From 2 raised to power 8 to 2 raised to power 15, that's monumentous. That's a lot. That's a lot. 2 raised to power 8 and 2 raised to power 15. That's a lot of difference. So we are seeing here that dimensionality is playing a lot of role here. And that's important to know in any optimization scenario, in any search scenario. Dimensionality, how many number of parameters you can optimize at one time. This will have a lot of time. This will have a lot of impact on your computational budget, on the quality of the solution, and so on. So dimensionality is really important. Yeah, so major takeaways from this talk. I don't want to go to a lot of technical details unless someone is interested, because as I said, the point here is not for you to know everything about it, but you have to know that there are optimization scenarios where uncertainty and noise plays a huge role. And I gave you some example in defense industry, in automobile manufacturing. These things are very important. So that's what we refer to as robust optimization, which is to say optimization under uncertainty and noise. Then we have a choice of robustness criteria. It's in practice quite important, and there are three main reasons for that. Computational aspect: you want to find out a solution if you are an engineer or designer as quickly as possible. You want to reduce your time to market. You want to reduce that. I mean, think of it as like this: every year you have a new car model, and if you take a lot of time to come up with the best possible solutions, you need to optimize each one of the individual aspects of the car. I mean, a car has multiple aspects, right? A car hood design, for example, the hood of the car, that plays a lot of role on the weight, the engine, everything. You want to optimize each one of them individually, and you want to do that as fast as you can, because if you don't, then you have competitors who will come up with a new model very quickly, and they will engage their customers. They will have a much more customer base, and so it affects the business needs essentially of each one of these automobile manufacturings. Your time to market has to be lower, so you want to focus on computational aspect. And let me also emphasize a little bit more on this. If the problem that we will, I mean, in this talk, I just described some of the interesting problems, like for example these ones. But these are academic problems. In industry, I mean, this is just to simplify the talk. But in practice, the problem that you are going to face here, they have a lot of simulation behind them. For example, when you're designing a car, one of the most interesting thing is to come up with crash worthiness. So you simulate how your car would look like by actually crashing it into a wall. There are physical simulations that actually do this. Companies do this, but there are also computational simulations. Because how many cars are you going to destroy like that? 1, 2, 10. You can't. You have to run millions of simulations to have a concrete answer, and each one of those simulations takes a lot of time. You give it certain parameters, design parameters. For example, you can say this is how my material is going to look like. This is the quality of my material, and now can you simulate and give me how would it behave, if there is an accident. And this simulation then would take a lot of time, and that's the main problem here. Computational simulations are very heavy. Computational fluid dynamics simulations are very heavy. So that's the point. Computational aspects are really important here. But there are other aspects as well, compromising on optimality, as I said, because now you have a new problem landscape. It will change the original one. But you are optimal. Maybe you are going to compromise on optimality. For example, if without accounting for robustness and uncertainty, maybe you would have more fuel consumption. But the fact that now you have to also, take that uncertainty noise into account, maybe now you would have a higher fuel consumption. So you have to accept that, because then you want to make a safe car, right? if that's what your goal is. I'm just saying that you have to compromise on something. And of course, the characteristics of the new problem landscape. And what we have seen here in this talk is that this worst case scenario, this mini-max robustness, is a preferred choice in the context of computational aspects. So if computational simulation, all of those things are really what you care a lot about, then minimax robustness is usually the way to go. So yeah, that's a little bit about that. That's an encapsulation of a very large study. We spent a lot of time on this, almost 1 year, but this is the crux of it. So yeah, so it's a pleasure, and happy to answer any questions that anyone might have.
Very nice, very nice. Thank you, Sibu Saab. Thank you for the detailed discussion. And some questions I have. For example, you mentioned definitely dimensionality is very important in regarding the computational time and budget, and it's very inspiring. You mentioned in the end the case study.
Mhm.
So now my question is, for example, the for the normal, normal computation time. What, how much is the normal computation time, and how many normal parameters for the as the dimensionality? Is the trend nowadays. I mean, definitely you can
Yeah,
include as many as well. What is the trade-off? Trade-off, something like
yeah.
that.
Like let's see. So what it depends on your, of course, it depends on what industry you're talking about. Let's talk about automobile manufacturing. So
Yes.
in the process of making the cars, and in the process of making the car, again, a car has many components. Let's say, for the sake of argument, a study that I did in the past, which is designing the hoods of the car, right? The car hood design, and the hood of the car has a geometry. It's a you have a 3D geometry, and you have as many number of parameters as you have the number of geometry points. A geometry can have thousands of points. So the first thing that you want to do is to minimize that, is to have less number of parameters. So for that, we also did a separate study on that, which is dimensionality reduction, which is to say that instead of all of those thousands of points, a geometry has thousands of points, right? You can think anything, you can optimize anything. You can change any shape. Uh, so the first thing would be to come up with a method to reduce the dimensionality. Then you can come up with 5, 10, 20, 30, depends on you. But if you have less number of dimensions than before, you're almost always going to lose some information. You're almost always going to have some noise, new noise. And so you have to come up with what would make more sense. Again, practitioners, engineers who have done this for years know this. But for example, you can have 10, 20, 30 parameters out of those thousands of them, and then basically try to optimize, with respect to that. And yeah, that's it can work. But the core thing here is to know that anytime you also do dimensionality reduction, you lose a piece of information that you can never recover.
That's nice. And also you mentioned about the 15 runs. Why
Yeah,
choosing 15? I mean, why not 10, 20, 30, or etc. something?
this is the reason for 15 runs is that if you do it only once, then anyone can say why one run. I mean, your results are not reliable enough because you have only done one run. Of course, you could also do hundreds of runs, thousands, but each one of them already took a lot of time, multiple days for us to do this. So 15 was just an acceptable compromise, just to say that our study or our results are somewhat reliable. But again, yeah, you can never say, for example, 10 runs, 15 runs, 100 runs, you can always do more. But the point is to be just reliable enough to have some confidence into your results. So so 15 seems just okay for us.
Yeah, that's good. That's good. And also, what challenges you have faced when applying AI in industrial engineering, particularly in Industry 4 context? Just you already mentioned some, maybe just to briefly mention now.
Yeah, I mean, like AI has grown out in recent years. Now we have much and more focused on the LLMs, so large language models, ChatGPT. I mean, those kind of things. So there's a different aspect to it. What we did is not related to that. What we did is basically applying AI in actual industry, actual, one of these scenarios. Like for example, I gave you some example on automobile manufacturing. There's also steel production. That's quite important, and one of the pain points of the steel industry, because the low quality steel they produce, or for example, if there are a lot of emissions, carbon emissions. For example, we have Tata Steel here in the Netherlands. Tata Steel, they get millions of euros of fine because there is a lot of emission from them. So they want to optimize their process to reduce those emissions, so that it has less impact on the outside environment. So yeah, the in the industry, in practice, it depends on what industry you're talking about, but each one of these industries has some pain point, and that pain point, of course, you can know more about it if you actually talk to the domain expert, or if you actually happen to know a lot about that industry yourself. But in practice, we saw these issues, for example, with Tata Steel, with the with Honda, for example, this point that they want to come up with a new design of cars as soon as possible. Efficiency is very important. Yeah, I mean, in the case of house building construction, stability, reliability, structural strength is very important. So yeah, every industry has its own pain points, and I honestly don't know a lot about every
That's
industry.
right. That's right. That's good. And also about, for example, about your Renewcast, this venture where you are the co-founder. What
Yeah.
makes this AI models of Renewcast outperform existing benchmarks in the day-ahead energy forecasting market? I mean, how it is outperforming the existing benchmarks?
We have normal energy forecasting usually depends on the farm level. So you have a wind farm. Imagine that there are hundreds of square meter. I don't know. It's usually hundreds of square kilometer, to be honest. And there are, for example, 20, 30, 40, 60, 70 turbines, assume. Then what people used to do before here is make one model for the entire wind farm. Just look at the average wind speed, for example, for each in the center of the farm, and then make a model on that. What we do here is we basically tailor ourselves in a way. We try to have as much information as possible about each individual turbine. And the reason why that is the case is because each individual turbine can have much more impact. Assume this: if there is a topology, if the topology is mountainous, then one wind turbine that is on the top would not behave as the same as that is below it, right? They will not observe the same wind speed, so they will not have the same air density, they will not. So having individually tailored information about each one of these turbines gives us much more information and power to you know to come up with
Yeah.
models that are usually more reliable uh, than our competitors in the past.
Yeah, that's good. And because each turbine, if you have the multiple turbines, definitely there is a wake effect where the front line turbines power production will be different as compared to the next line. So there is a wake effect analysis. Definitely, you are right. Multi turbines impact. That's good. And what are your biggest learning as a technical co-founder, managing both research and development and product delivery, something like that? How? What are the biggest learnings you mentioned, please?
I think it depends on the startup journey. It depends on where you are in your startup journey. When you are at the beginning, the when you're at the beginning of your journey in a startup, the biggest problem is always money. It's not the technology. It's nothing else. It's always the money. Because if you have money, you can always go ahead for next 2 years, 3 years, 5 years. If you don't have money, you have to usually make very hard choices, and none of those choices are easy. And if you do make any one of those choices in a wrong manner, you are sometimes the results are catastrophic. You just have to go out. So at the initial stage of your journey, it's always about the money. Once you have a seed round, once someone has invested in you and you have some leeway, a runway for next 2 years, 3 years, 4 years, whatever, then the biggest problem, of course, is making the product market fit, if you would. Then you really have to validate that your product is good enough, it can scale, you know and you have to actually do this not by asking questions. You have to actually build that stuff and then go to it. So, and of course, keep optimizing, keep do this interpretation. So, and once you are even after that stage, once you have found a product market fit, then the third problem is always with the scalability. Now there will be a lot of customers waiting for you. Can you satisfy all of them in an efficient manner, making everyone happy, or at least as most of them happy, so that they come back to you? So scalability has its own challenges. If you can have a really nice, beautiful AI for 5 people, it's different than serving 5 million people. So that's then usually the third one, and after that, then there are other issues. Having an organization, having a legal structure. You want to be as flat as possible. You want to be as efficient from an organizational point of view, and then you have to go to other markets, not just where you're performing. So every stage has its own issues.
Yeah, nice, nice. That's nice. And what would you advise? What advice would you give to the students or early career professionals who are interested in applying AI to real world problems?
Yeah, well, I would say first of all, align it with your business goals. What are your real business? What do you really want to accomplish? What do you really want to achieve? Learning is okay. You can do Coursera. You can learn online. That's no problem. It's always a good thing to do. But if you want to really apply and you have high expectations from that AI in terms of business, in terms of the fact that it will give you money in some sense, then you have to align your requirements, your goals, your business goals with what you have uh, you know, with your AI. Then the problem here is the second problem usually is once you have defined this, and there is a lot of support from the top for you to actually implement, execute this. Then the second step usually is, and it's quite difficult, garbage in, garbage out. AI is basically empirical models. AI is nothing. AI it's nothing magical. AI is most of these AI models, assuming that they are neural networks based, deep neural networks based. They're empirical models. Garbage in, garbage out. But if you train them with a bad data, you're going to have bad results. There's nothing magical about it. And then there are ways to actually increase the data augmentation techniques. But that's a separate subject. The point here is garbage in, garbage out. You have to have really, you need to invest a lot to have good quality data so that your AI or the models can actually learn something from it. And yeah, then the third thing would be to basically integrate all of this in your daily processes in your company or where you work. And that's again not easy because old processes have to be changed or modified, and not everyone is happy about it. You know, some people would lose their job. I mean, I'm just talking about all of these aspects. So yeah, usually when you are applying to your business, first thing would be to align it with your business needs. Then garbage in, garbage output. Invest in clean data. Invest in a clean data ops strategy on an organization level, or at least a team level. And then third thing would be to basically whatever AI eventually gives you, and you will optimize it with time. You have to then integrate it with the existing processes and systems, and that's not an easy task.
Yes, yes. And also, I heard that the organizations in Europe, they are working on data collaboration. I mean, will share with each other, because there is the main problem of the data you already mentioned. So, okay, that's good. And what skills do you consider non-negotiable for future AI engineers working in smart industries?
Uh, I would say focus. Well, one of the worst thing that has happened since ChatGPT came on, and LLMs became so ubiquitous, if you would. One of the worst thing that has happened is that coders, the programmers, they don't actually now program a lot these days. They just go to AI and ask that to produce it, and it usually is quite reliable. And but it does change the way that you approach problem solving. If you're not doing it yourself, it's fine to do it, of course, sometimes, but don't over rely on AI. Build your own skills, because AI will change. I mean, this is not the end of the AI. There will be an evolution. Okay, we will move from A to B, and then from B to C. It's continuous. It will not stop. So, but this is, if ChatGPT, if you only use ChatGPT, and then and then there would be another day, another model, DeepSeek, that will change the way you work. So don't rely too much on the AI. Build the actual core skills. Learn the way the models work. Learn the reasoning behind why they work, and a little bit of mathematics. You don't have to be a mathematical guru. I mean, no one knows every detail. Believe me, even in a camp, no one knows every detail. But you have to know enough to know how a model works, and at least on a conceptual level, if there is something, if you want to tweak or fine tune, you can do this. So I think the main point here is to not rely overly on AI and basically have your own hard skills in this field. So
Yeah, that's good. And thank you. Let's end this session. Sibghat Ullah Thank you very much for this inspiring your academic journey and then entrepreneurship journey is truly inspiring. And also, we appreciate your time and hope to collaborate again in future, inshallah.
yeah,
So, any comment from your side? Let's end this session. Thank you very much from my side.
yeah. Thanks a lot for inviting me, and happy to be here. And yeah,
Thank you.
let's
Have a nice time.
yeah.
Have a nice time. Thank you.